complicated, hung up and miseducated.
Hello everyone, welcome to Automata 101, the Undecidability and Intractability edition. To start off, let's have undecidability first. So what's an undecidable problem? Well, basically, it's a problem that has no algorithm or decider Turing machine that can solve all instances of the problem, though it can create algorithm or decider that will work for some instances, but not all. So to further explain what an undecidable problem is, we have the busy beaver problem. This problem was discovered by Tibor Rado, a Hungarian mathematician, in May of 1962. This problem requires a bit of knowledge about the Turing machine, so doing a quick recap about what the Turing machine is will be very much helpful. And now going back to busy beaver. You might ask, among all animals in the planet, why a beaver? Why was it even named that way? Well, maybe because a beaver perfectly fits the role. Just try to imagine a busy beaver running back and forth across his dam, making tick marks in the wood, and sometimes is in a confused state on what he will do next until he gets to see the tick marks next to the one he just made earlier. So why is the beaver problem undecidable? To put it in a much easier perspective, this problem was able to decode only three values of b of n. b of 2, which is equals to 6, b of 3 equals to 21, and b of 4 equals to 107. For b of 5 and b of 6, these values are yet to be discovered. Imagine 47,176,870 and counting, or a 3 times b of 6, which we do not even know the exact value, is greater than 3 times 10 raised to 1,730. Therefore, this is a simple way of explaining that the beaver problem is undecidable, since it does not have a Turing machine that computes b of n for all instances of n. We now proceed to some examples. Note that these examples are just snippets of the problem, wherein we are asked about what is the maximum number of ones that get printed on the tape for our given Turing machine when it halts. So for the answers, I've already mentioned them a while ago. It was the values for b of 2, b of 3, and b of 4. So my main point for the given examples is to just simply show how the busy beaver problem works and somehow prove that as of now the beaver problem is still an undecidable problem, since the Turing machine cannot compute b of n for all instances. For number 1, we have the input binary numbers 0, 1, 0, 1. So what the busy beaver does first, when it sees a 0, it will point the pointer to 0. Next input is 1. When it sees a 1, it will change 0 to 1. Next input is 0. When it sees it, the pointer goes left. Next input is 1. When it sees that, it repeats processing 0101 again. But before doing that, it changes the 0 to 1. This will therefore show that the value 0101 is just one of the many values that will sometimes not halt in a busy beaver perspective. For number 2, we have the input binary numbers 0110. 0 will be our first binary number input. It simply does the same thing. When it sees a 0, it points the pointer to 0. Next input is 1. When it sees this, it changes 0 to 1. Next input would be 1. When it sees this, now instead of going left, it goes right. And finally, when it sees a 0 and detects that it's the very last input, it halts. This will also show that the value of 0110 is just one of the many sample values that may possibly halt in a busy beaver perspective. And that proves our point that the busy beaver is an undecidable problem.
Intractability. So we're going to define what is an intractable problem. It is a problem that has an algorithm to solve it, but no matter how clever, it still runs in at least exponential time. Therefore, the algorithm is unacceptable. For our example, we have the Hamiltonian cycle. It is a cycle in an undirected graph that visits each vertex exactly once and also returns to the starting point. It was named after Sir William Rowan Hamilton, who devised a puzzle in which such a path along the polyhedral edges of a dodecahedron was solved, or the Icosian game. We have a graph G, and it contains a Hamiltonian cycle. From vertex A, we go to D, to C, to B, to E, and then go back to A, which is the starting vertex. We can also have A, D, E, C, D, A, or A, B, C, D, E, A. So why intractable? Given a graph G, we find a Hamiltonian circuit. And the only way to determine this is to do a complete and exhaustive search, or doing brute force, to find one that visits each vertex exactly once. Our worst case here is to search through all paths. So in our previous graph example shown here, how many paths are there? So we're going to show these paths as a search tree. Since we have to list all paths from A, this approach will take exponential time. So let B be the average branching factor of each node or vertex in the tree. So V vertices each with B branches. So the total number of paths is equal to B times B times B, and so on, or it is equal to the big O of B raised to V. Searching through all paths and verifying that it visits each vertex exactly once would take at least exponential time.